Assalamu alaikum, greetings. So in the last lecture we talked about Fourier transform. Now this lecture looks at the impulse function. Now the impulse function, it's extremely important and merited its own lecture. Now an impulse function is, simply put, a high burst of energy, a massive burst of energy in a limited amount of time. So, for instance, these two pictures that you see here, where Batman is punching and there's this loud kapow that you hear, and here it's Robin, and whenever he punches, there is this pow, which is shown on the image, is an excellent example of an impulse, where impulse is something hitting a very fast burst of energy observed in a very small amount of time. And that's what's an impulse. Now, what is directly related to an impulse is how the system behaves in response to an impulse. Now, what do I mean by that? So, for instance, if you're given a gift and you have to determine what's inside the box, you're going to move the box a little bit. And the movement of the box will allow you to hear something. So you're going to tap the box, you're going to give it a small number of taps, and those small taps, whatever voice that comes out, whatever echo comes out, if it's a jingling sound that you know there's something like maybe there are a bunch of coins in there, maybe there's a bell in there, or maybe there are a bunch of bells in there, or let's say you hit something and there's a lot of toys there that if you press a button they will make a sound. So effectively what you're trying to determine is what is the response of that system, in this case that will be your box. So your box is the system, and what you're really trying to determine is the response of that system to the impulse, or the series of impulses that you are presenting to the system. That's called the impulse response of the system. Now, an impulse, again, the concept is it's a burst-like energy in a very limited amount of time. The interval is close to zero. It's like a smack. It's very small in duration, and it's a huge burst of energy. The amplitude is 1, or you could say that the total energy, the amplitude is not 1. The total energy of the impulse is 1. That means that the amplitude will be directly determined by the interval. So in this diagram, for instance, if the impulse varies from minus t by 2 to t by 2, then the entire region, this will be the amplitude, such that if I multiply or find the area underneath this curve, it's going to be 1. If I reduce the interval, then the amplitude will go higher, such that the area underneath this curve is 1. If I reduce the amplitude further, if I reduce the interval further, then the amplitude increases proportionally, so that the area underneath the curve remains 1. In other words, in all three instances, which are shown in diagram A, the energy of the signal is independent of the time duration. It's independent of the amplitude. The energy of the signal of an impulse is 1. So, for all effective purposes, again, the concept is the same. It's like Batman hitting someone and you hear the sound kapow. The duration is close to 0, it's approaching 0, and therefore for all practical purposes, the amplitude approaches infinity such that the multiplication of the amplitude with the interval is equal to 1. Now, to have a meaningful visual representation, we see an arrow which points to infinity, but usually you stop at 1. That's the mathematical, or at least the meaningful representation of an impulse. So an extension to this same is that if you integrate this impulse signal in the time domain, you get the energy 1. The 0 plus 0 minus shows that the duration of the signal in fact is very small, yet still the energy comes down to be 1. Here we are going to represent the impulse signal by dt. Now in this instance, which is an extremely useful property, what it says that if you multiply if you do this with a signal gt in relation to an impulse, what you get is the amplitude at that signal at instance 0. Now this is the same impulse signal, but it's shifted in time domain by t naught. Now if you do this with a signal of gt, then what you have here is gt naught. In other words, you capture the amplitude of that signal at instance t naught. Now these two particular properties are very important in determining in linear time in linear systems. Now in linear or LTI, so a linear system is that given an impulse, the response of that signal is gt. So this gt is the impulse response of this system. Now, any signal going from this previous, any signal is basically can be determined by shifted impulses, because the impulse is going to capture the signal at time instance 0, and a shifted impulses will capture the signal at that instance. So any signal can be generated by a series train of impulses with different magnitudes. And that's exactly that's why for a system, if you need to know how the system behaves, that is modeled using an impulse response. So if you have an impulse and you have the response gt, if you increase the magnitude of that impulse by a constant k, the output also increases by the same constants. This makes it a linear system. In a time invariant system, and most of the undergraduate talks about LTI systems, linear time invariant systems. So in a time invariant system, so if you defer the impulse by a duration tau, the output also retains the same shape, and it is also deferred by the same amount tau. So this makes it time invariant. The signal doesn't change their shape because it is deferred. The signal shape remains the same. Now this is an example of linear. The constant k is the linearity component, the time invariant component is t minus tau. So it shows here that if a signal for an LTI system, changing the magnitude by k changes the output by the same magnitude k. So it is linear. And deferring the signal by tau defers this output by a similar component. Now this is an LTI system, and most of the systems in undergraduate are in fact LTI. This is where things can come out to be. So this is the convolution of a signal with the impulse response of that signal. So the output is directly related, or is the convolution of the signal with the impulse response of the system. So that's pretty much of the impulse function. Next lecture we're going to talk about discrete Fourier transform, or some properties of Fourier transform. Thank you very much and have a good day. Assalamu alaikum.